How many random zeros I
Silence.
Oh, I'm sorry. What was the? What was,
Did you behave yourself at the DM meeting?
no, I misbehaved in all sorts of ways.
I assume that would be the answer.
Should I be standing on the other side of the screen?
You should go wherever you are, where you feel
I'm just trying
comfortable.
to figure out like where it's in camera.
Right.
What camera is being recorded?
He's screen sharing. I'm gonna turn mine around for person thing.
Morning, Josh.
Okay. Hi, Yusra. Good morning.
So we did make some progress.
Morning, Frosty.
But I got it to where and put the pointer in the middle.
We're just gonna give it 3 more minutes, so then.
Yeah.
Unless you want to paste,
But
which is
in
fine.
the
Yeah.
process, I discovered that I think some significant redesign needs to be done.
I was afraid of that.
Oh, what about?
Well, the leaflet-related stuff.
You're gonna start with Jonathan at some point and show him.
Yeah, that'd be great.
Look at all those Arizona people on that list.
And say again?
Look at all the Arizona people on that list. Roloff was a postdoc. Stefan was here.
Yeah, I agree. I'm Jonathan, by the way.
Hi, Ed Belchevsky.
Nice to meet you.
Tim Axelrod.
Nice to meet you. Yeah, Stefan has said wonderful things about Tucson.
The problem is there were so many Stefans
So
and
anyway,
Stephanies
I kind
Oh,
of
in our
decided.
grad program.
Yeah,
It's
so
hard for me to
The
remember.
issue,
Okay.
how projections are dealt with in the layer.
Roloff was.
Are you on the network? Have you established that you're on the
I am,
network?
yes.
Yes, and there seems to be some, there's the thing about the transform not being in there, and there's even some confusion about which direction things are going from what this turns out that what it's really expecting you to give in the GeoJSON thing is
Do not disturb. Are you in Do not disturb?
I pinned that on.
Good man.
Right.
Don't be
I
mean.
like learning that around.
Yeah.
No, not, it's not the ordering of lat versus long, it's the type of coordinates. It's really expecting X and Y just because of the way it's.
Should I be using my
I
laser
see.
point things
And I don't think that
Yeah.
was the
rather than
intent.
a laser point?
Yeah, I think that's
Lots of
fair
big
because
ones
then
because
it's
it
recorded
makes
on the
a lot of
screen.
sense.
So.
Yeah, so-
But they're invoking the transform.
So I'm not sure if
in
it-
the wrong direction.
Let's make
If it
sure it's
doesn't,
so,
just
yeah.
just do the
So it just-
we'll have you on.
it just-
I'll turn around and have you on.
Yeah,
You
it reaches
with the
point
screen,
where I
so
sort
the
of ran
laser
out-
pointer will still
ran out
be,
of time
I think, useful.
to fool around with it.
All right, 11 o'clock. Let's see if I can do this thing. Okay. All right, let's get the show on the road. So, good morning. This is an LSST Tech Talk, continuing the program of having talks about software and IT topics that are relevant to observational astronomy. And tonight's guest is Jonathan Sick from Queen's University. And over to you, Jonathan.
Great. Well, I want to thank Frosty for inviting me here and all of the LSST team. It's been really exciting learning about the project. And yeah, I can't wait to start contributing to it. So I want to talk about the project that I've led for my PhD thesis, which is Androids, the Andromeda Optical Infrared Disk Survey. This is a project we've done with the Canada-Francois telescope to map the entire bulge and disk of M31 across 14 square degrees of the sky and 6 optical and infrared colors. But the framing for this talk is really about how we actually put together the survey. So I see this as being sort of typical of the next generation of, grad student type projects where, a small team is getting huge amounts of data. So it's not unreasonable for a small team to get 100 hours of observations or to go to an archive and download, terabytes upon terabytes of images. And the question is, how do you actually go from data to results? There's no framework to date, I think, for doing these types of reductions and analyses. And so it's meant that I've had to come up with my own solutions. And so in this talk, I'd like to show you how I've gone about this And then what I'm really excited about is how LSST is putting together an API and framework for putting together pipelines. And so in the end, I'll actually talk about how I think LSST can help in this type of work. So before I get into the tech stuff, I'll start with the science framing. So why did we need to go to M31 again? It's been a much studied object. And of course, the great thing about M31 is it's close, so you can resolve stars in it. But it's even more special in terms of being the closest massive disk spiral galaxy. So here we have a galaxy right on our doorstep that has an extremely complex star formation history from galaxy mergers and secular evolution. So here we can actually see the complex types of galaxies we can only see otherwise in more distant galaxy surveys. So that means that with its proximity, so being able to look at resolved stars, we have different ways of actually looking at M31. So we can look in terms of resolved star populations. So that's what the panchromatic Hubble Andromeda Treasury Survey has done, to see resolved stellar populations and get a really deep sense of what the age and metallicity evolution of the M31 disk is like. We can also look at how individual stars move and build distribution functions for the bulge and disk and halo of M31. And you can't do that in most other galaxies. And you can also go through the entire halo of M31 and count individual stars in that halo, covering huge swaths of the sky to map the actual accretion history of M31 in its halo. And so again, this is unique to M31, of this type of work we can do. But my tact has been, how can we use M31 to actually understand these more distant galaxies where we only see the integrated light? So essentially, how can we bridge these types of analyses to the types of analyses we can do with LSST, for example, integrated light of deep galaxies? So to do that type of experiment, you actually need a very basic piece of data. You need to actually be able to look at M31 as if it were a more distant galaxy. So we're actually missing this piece of data. We're actually missing basic images of M31 in different color passbands through the optical near-infrared. Now, of course, Sloan has tried to do this. Those images are too shallow. Compared to CMD fitting for resolved stellar populations. So we can actually do that on a pixel-by-pixel basis by looking at the star formation history inside a pixel and comparing that to the actual stars we see in that pixel. And then you can go even deeper in this by actually identifying the tensions in stellar population synthesis. So right now, there's actually a big issue in terms of the near-infrared. So the near-infrared should be great for actually breaking degeneracies of a galaxy's color with respect to its star formation history, its metallicity, and its dust content. So we absolutely need the near-infrared, but at the same time, there's been a chorus of astronomers and teams and papers saying we actually don't actually know how to use this near-infrared data. So in papers that are looking at the masses of disk galaxies, they've actually said let's ignore the near-infrared data and only look in the optical. And the reason for that is because they're thermally pulsating AGB stars, which contribute a dominant amount of light in the near-infrared. Over 50% of the near-infrared light comes from these types of stars for intermediate age stellar populations, and yet we don't actually have good models for these types of stars because they're undergoing these thermal pulsations, which we can't model on computers very well. So a really good demonstration of this problem came from the Gamma survey, so Taylor 2011. And what they've done is fit the SEDs, the special distributions, for SDSS and Euclid observations for tens of thousands of galaxies. And what you're seeing here is actually the residuals of their SED fit in each individual passband, and then the shifts here are due to redshift. And what they're saying is that if you fit only the optical portion of the SED, so U through Z band, you can fit the SED fairly well. Of course, the U band has fairly large residuals because of dust, but they say you can do a very good job. But then if you include the near-infrared in your SED fit, then the residuals increase across the board. So what they're saying is you can't self-consistently fit the entire SED of these galaxies. So why is this? Well, of course, it could be because we don't know how to actually deal with near-infrared isochrones, stellar populations. It could be that since we're actually breaking degeneracies in star formation histories, perhaps we have too simplistic parameterizations for these star formation histories, so exponentially declining star formation rates. Perhaps we need something more complicated than that. And you can sort of see that might be true because the optical actually has no information that predicts what's happening in the near-infrared, just given by these massive residuals here. And another issue is just be how do we actually match near-infrared and optical observations? And so I think for this particular survey, this was a dominant contributor for the error, but I would say that we still don't have a good sense of what's happening with TPADB stars, for example. And so that's the beauty of this type of work, is that with M31 we can map SEDs across all these pixels, and then we can go inside the pixels and look at actually what stars are contributing to that light, and do a direct calibration of these stellar population synthesis codes.
What's the significance of the dotted dash curves there?
So the solid is the, I guess, the 50th percentile, so median SED, or sorry, residual in that SED bin, and then the dashed would be probably 1 sigma. Yeah. So to build this type of data set, we went to one of the best wide field observatories in the world right now. One of the best. So the Canada-France Hawaii telescope, which is perched beautifully on Mauna Kea. This is one of the pictures that I took. And so we've used both megacam and weircam. So with megacam, it's a square degree imager. So on the UGRI bands, we can cover 14 square degrees of M31. So that gets us out to 40 kiloparsecs in the major axis. And then using weircam, it's a slightly smaller detector, 20 by 20 arc minutes. And so we cover in J and K bands out to about 28 kiloparsecs in the major axis. And so as you can see, this is a massive superset of what the Hubble Andromeda Treasury Survey can do right now. So we're really getting the entire bulge and disk of M31. And because of the natural seeing on Mauna Kea, we look at resolved stars in M31. And because of the work that we're doing with background calibration, we also get SEDs across the entire disk. And so it's this combination which is unique to this survey. So this is what the data set looks like. It's just an incredibly beautiful data set. As you can see, it's massive on the sky. So here's the full moon to scale. And in this deep stretch, you can see that we actually are footprint limited in our surface brightness calibration. So we can actually see isophotons going all the way up to the edge of this footprint. So here at the edge, we're going down to 26 meg/second square in G-band. And let me just zoom into one portion. So here's, we go into the star-forming region here, we can zoom in, beautiful data set, and the UGR bands. Then we can look in the near-infrared, and now these are all AGB and RGB stars that are popping out. And if I can get this to work, we can even zoom through the data set. Oops. Right, so here's a TIFF image live rendering that we can go through. So you can zoom in, and it's just a breathtaking data set. You can go in to within dust lanes, see individual resolved stars, and you can just cruise around seeing individual star-forming regions. Let me zoom out slightly. And then what's amazing that we learned about M31 by doing this survey is that there's just star formation everywhere, even at large radii. So here is the star formation region at 10 kiloparsecs, and then going up to 15. There are background galaxies that we see through the disk at M31. And then we just keep going along the major axis, and they're just star-forming regions that pop up everywhere. So another background galaxy, another star-forming region at probably 20 kiloparsecs. And then let me just skip to the end here. Is it even at nearly 40 kiloparsecs? We see star formation happening in these small regions. So So by having a survey that goes to this type of depth and breadth, we can really, truly see what's happening in the disk of M31 and truly appreciate star formation that's happening at large radii. And then I can also go into the near infrared. And what I just want to show you is the near infrared, of course, seeing is much better. And so again, if you just zoom into the disk, these are all RGB and AGB stars that just pop out. Okay. But now, so it all looks fantastic right now, but what I want to give you an appreciation of was that it wasn't all rosy from day one. So when I first started grad school, I went to my advisor's office, and we looked at some data that he had obtained just the semester before I arrived. And this is what a calibrated WIRCam image looks like coming from the CFHT pipeline. So here's M32 right here. So okay, you can see M32, but the center of M31 should be somewhere up here, and there should be a beautiful gradient from the disk. You see no such thing here. Even though this is flat fielded, there's dust donuts in the optics, there's all sorts of artifacts in the detector. So we knew from day one that we'd actually have to go from nearly raw WIRCam data and megacam data all the way to producing, SED and resolved stellar analyses. We'd have to build an entire pipeline for the survey. So what we ended up doing was building a stack, much like an observatory would do. So our approach for this was to use Python everywhere. And so the advantage of Python is that you can build systems. So Python is a very general language, meaning that you can do numerical work, you can do systems integration work, you can even pull out to make web applications and services. So it's a very general language and effectively the de facto language for observational astronomy right now and in the future. So the approach that I took was to have, essentially a proprietary application layer for the actual pipelines. We have one pipeline for the image calibration and mosaicing, one for the SED analysis, one for the also population work. And then since we're in Python and open source software, we can build upon lots of Python packages. We can integrate lots of command line programs and then work with databases as well. So this is the type of environment that we're working in. And then one of the key decisions early on was to say as much code as possible should be open source and actually extracted out of these main pipelines. So this is something that most people don't do right now for the most part. But the advantage of this was giving the project visibility on GitHub, and also making generic packages increases the quality of your code substantially. And so for the open source packages that I created, some of them are bridging to stellar population synthesis packages in Fortran. Some of them are calling databases. Some of them are just interacting with command line programs. But the entire idea is to have an integrated Python environment to do this analysis so that everything is in code, everything's reproducible, there's no steps you do by hand that you essentially don't remember how you did. So that's the key behind this pipeline.
Are you going to briefly tell us what some of these things are? Because like Shapely, I had no idea what Shapely was.
Yeah, I'm not going to get into detail of all this stuff, but for example, Shapely is a 2D geometry package in Python. So what that lets you do is, and it comes from the geoinformatics community. So you can do essentially unions, intersections of polygons or points, and so that's used for basically to deal with footprints and figuring out what's inside different combinations of fields and creating like that. All right, so how do you actually build pipelines? So when I started grad school, there was actually no documents written for how the average grad student builds a pipeline and does this.
Or even anybody at all.
Or even anybody at all. But the initial, in second year astronomy lab, what we were taught is if you want to do massive data processing, you write a script and then you feed it in paths to text files. And so this is actually the state of the art as of my undergrad, and still for most people today, this is the state of the art. What you can appreciate is this doesn't scale once you start having more than a small directory's worth of images. So even with the survey, even with one person working on it, we have several thousand WIRCam integrations covering many fields. We have lots of megacam integrations. It's a fairly heterogeneous data set, so I've included stuff from the archive. So there's different observing strategies. There are sky fields used for calibration, there are disk fields, so you treat different data sets differently. And so the key problem was how do you actually keep track of all this data, and how do you keep persistence and state within your pipeline, so you actually can keep track of all the metadata that you're building as you process the images. And so again, this is sort of what I term like a medium data problem. Is we don't have to go to the NSF and ask for massive budgets to deal with this type of data. Everyone needs to do this type of work, and yet, somehow you have to make it work. And so to deal with this metadata, the first thing you can ask is, well, maybe we should build some sort of database. And so the normal answer is just go to SQL, build a relational database, and you can store anything in SQL, of course. But the problem with this is everything comes down to schema, and you actually have to know what you're doing sort of from the outset, or at least have some sort of plan. But the problem was with this pipeline is, first year grad student, I had no idea what I was doing. I had no idea what type of data I would need to retain, and what the general schema for this sort of database should be. And so what that meant is that every step along the way, every new piece of the pipeline, I'd have to do some sort of migration. And so 2,000 migrations later, it would work, but it would be a lot of work. So then, I had my ear to the ground of what was happening in sort of the big data tech scene in New York and San Francisco. And this was the cool thing that was coming out. MongoDB was part of this whole notion of no SQL. Let's get away from these relational databases with strict schemas. Let's just store everything in a database. And the idea of no SQL probably scares a lot of people who are used to relational databases, but this actually maps extremely well to this problem of how do you be a single astronomer, trying to build a pipeline in an agile way, just make it work. So this is what our MongoDB database documents look like. So essentially, MongoDB it's a true database server. So you have some server that you connect to over TCP. It has a database, and then these collections are essentially what you have as tables in the relational database world. And then within these collections, you have your documents. And so essentially, every piece of every atomic piece of data we have in our pipeline, so all the images or mosaics or what have you, they're essentially mapped to MongoDB documents. And that lets us keep track of them within the database. And so, for example, if we want to keep track of all the raw integrations, is we have a MongoDB document that looks like this. And what this is it's just JSON for those who program for the web, so JavaScript, serialized objects. And so it's key value stores, which map directly to dictionaries and ordered dictionaries in Python. So that means that it's very natural, it's very Pythonic when you're working with it. So every MongoDB document has an ID which identifies it. So we just use the odometer from CFHT to identify images, for example. And then as we obtain data, we ingest it. So essentially, we actually copy over all the header keywords. We no longer have to deal with FITS headers. We now deal with MongoDB versions of the headers. And we keep track of things like the paths to all the images in the file system. So we don't replace the file system. We actually use this as an index, essentially, of the data on the file system. And then what you'll notice is that MongoDB, without us having to say what data should be stored, you can store heterogeneous types of data. So you can store lists of lists if you want to have a footprint and a right ascension and declination. And then you can have embedded documents, so dictionaries as values of these fields, if you want to have some namespace structure. So for example, everything that's been flat fielded using night flats, the calibrations that come after that would go in this embedded document. So that way you can have actually parallel versions of your pipeline that have different namespaces, for example, that don't conflict with each other. All right, so again, MongoDB, the advantage of it is true database, so we can actually connect to it from different computers. So that means we have some sense of scalability, and it has a query language, which I'll get to in a moment. And again, the key is, even if you're not a fan of MongoDB, you have to admit that this type of data store maps directly, really well to the type of data that we're working with here, which is just, metadata keeping state of a pipeline. And again, it's schemaless, and the advantage of schemaless is that instead of having to do schema migrations, I just essentially write code that defines the schema. So the schema becomes idiomatic. Essentially, what types of data I want to store is what is stored in the database, and if I want to change that, I just change that. So I'm not doing schema migrations. I'm just, what the code wants is what actually happens in the database. So again, this just lets me experiment. I can build new pipeline steps, and then it just sends data to the database, and that's now effectively the de facto schema. So the querying for MongoDB is also very Pythonic and simple to use. Even simpler than I think than SQL statements. So if you want to query for all the images that have an object field of M31-1, so all the WeirCam images, say in this particular field of M31, is you just call the find method on your collection object, and you just queries are documents. So just dictionaries again, where you have the field, and then the value is M31-1. So this is essentially an equality query. Now, if you want to do something more sophisticated, like do an AND operation, so M31-1, and you also want JBand images. Do you guys use MongoDB? So how do you think that would be done, Frosty?
I passed as a pair.
Yeah, you just have two fields in your dictionary.
Awesome.
So what you expect should be true is actually what is true. And so what's really neat about this is you can build your queries just by doing updates of your dictionaries. So you just can have one dictionary with one set of selectors. You can have another one, and then you just join them together by doing a dictionary.update. Now you're building your queries that way within code. So it's really, really easy way to do things. And then you can have more sophisticated types of queries where you now use operators. So for example, if you want to do search for M31-1 objects, fields, and either J or K band filter images, now you actually use this in operator where you're looking for values of the filter field that are in this list. And so you have in operators, you have or operators, you have greater than, less than, so you can essentially build whatever type of query you want with these operators.
So that's a MongoDB in operators, not a Python.
That's right. So essentially MongoDB, there's this sense of you're building a query document, and so essentially, yeah, you have these operators within a document, and so yeah, and so you can go through the MongoDB documentation and see that you can build, really complicated, ORs or what have you, but it's a very simple query language to get used to, and again, these are just JSON documents essentially, so you can even persist queries inside databases and things work really well. So with MongoDB now as the framework for the pipeline, we can build pipelines that look like this. This is actual Python code from the stack that I just edited and put on the slide here. So how all these pipelines work for Androids is we start by, I should first say that what we're doing here is essentially finding sources in our images and then using them to do astrometry using the Astromatic suite, so scan and source extractor. So the first thing you'll notice is that everything is abstracted with Python objects and Python interfaces. So I've built code called MoAstro for MongoDB Astronomy Framework that actually has Python interfaces to source extractor and to scan. So that lets me configure everything from Python code. So again, I don't have configuration files, loose in the file system. Everything is defined within code. It's in version control. It's on Git, so I know what I'm doing. So how the pipeline works is you start out by connecting to something that wraps MongoDB. So we have an image log, and then this whole server thing just lets me sort of have a configuration for what server I want to connect to. So rather than remembering passwords and IPs and so forth, I just can connect to it that way. And then I define what images I want to work on. So again, we just build a dictionary that's our selector, our query term. So here I'm looking for all the MegaCam images. This field here, it's actually a spatial query within MongoDB. So that's another really cool aspect of it, is that it has spatial queries baked in. So if you use Foursquare, Foursquare is actually built on MongoDB. So what we're doing here is we're asking for all the MegaCam images that have center of their footprint within this 8x8 square degree box around the center of M31.
Is that spherical geometry or Cartesian geometry?
So it started out as Cartesian, but now they have true spherical geometry.
So
yeah.
If you're at the North Pole, it works.
It will work. Yeah. So this is using actually the old style of spatial queries. Now you would use I think like D within it or something, and you can do queries within polygons. You can do fairly sophisticated spatial queries. And then we also just do sanity checks. So here we have this exists operator that just makes sure that we actually do have a field that has a path pointing to this image on the file system. So we make sure that we're actually looking for images we actually have on our hard drive. And then the idea is that you pass, your connection to the database, the selector for the images you want to work on, and then fields within the database corresponding to the images that you want as inputs. So here we're rooting in, all the key path images, and those are inputs for the source extractor. And then we also tell source extractor where we want to store the results of the pipeline. So we want to store the source extractor catalog paths inside this SCAMP embedded document under the source extractor catalog path. So this doc here essentially maps to a document within a document, so a dictionary within a dictionary is the idea. And then so that means that we just run this, and then now our source extractor catalogs are mapped, their paths to those are stored in this field of the database, and then we can just pass that database field into the next process. And so this is essentially how I build pipelines, is we just have selectors and we have the fields as the inputs and outputs, and so you can chain things together that way. So again, this is the type of thing that that works as a small team to do this type of work. Now you can do more sophisticated types of processing with MongoDB, since it is an actual database that you can connect to over a network. So you can actually do things like, if you have a set of computers and you have a bunch of embarrassingly parallel tasks, you can actually use MongoDB to mediate and help you process embarrassingly parallel compute queues. So say you have lots of computers. Each one of them, you start up some Python code that runs this worker process, and then essentially how these queues work is you grab a document, which is your job, so claim document, and I'll get into what the claim doc function is. You process them, you store the results back in the database, and then you get the next job, and you just do this forever until there are no more jobs to compute. So the magic of this is given to us by MongoDB's atomic find and modify queries. So this claim doc is defined within this lambda function that I've defined right here. And so what it's doing is essentially each job is a document. And the documents, they could either be purpose-built just for this job queue. So I could have one document per job, or I could just have these jobs embedded within image documents. So I could have, every image, I have a job associated with it. And so I want to query through all my images and process them in some way. So the basic idea is that our worker function selects some types of images with this MongoDB selector, so again, just a dictionary. And then we actually modify it so that we're looking for essentially tasks that haven't been started yet. And so the way that I tag tasks that haven't been started is documents that don't have a task field in them yet. So it could be, it's very flexible, it doesn't have to be this way. So essentially we want to look for blank documents, but the documents will have some sense of input data for the job. And then what our claim document lambda function does here is it uses a find and modify MongoDB query. And so this is an atomic query, meaning that you can have 1,000 processor or 1,000 different cores call this query, and then MongoDB knows to actually work through them one at a time so that their results don't conflict. So what's happening here is it queries for documents that have, that fit the selector, and then as soon as it finds a document, it will return only one document to you, and as it returns it, it will actually do a modification. So it'll do an update. And so in this case, we're updating it to first create a field called task, and then have a field within that called task.started, so this embedded field here, and say it's true, and that completed is false. And so now that as soon as we grab a document, grab a job from the queue, we're tagging it and saying we started processing it. And then the cool thing is this is atomic, so MongoDB is just going to do this properly, so every core gets only a unique document, so you don't have duplication of work.
And this is true when you have multiple slaves?
Yes, so this is actually made so it can be. So I haven't done a lot of work with having multiple slaves, but I think you would want to have this routing to only one perhaps. Because it's true that MongoDB has eventual consistency rather than being an ACID database. So I think that might be how you want to do it. Yeah, that's something good to check. But the key thing is that this is extremely fast, and so I think you can just have one server, processing this type of work. And so now you process the document. Your processing function has some results, which are a dictionary. And then again, since MongoDB is just dictionaries, essentially, you can update your results with a field, task.completed is true, and then now you update the database so that then when another core does this find and modify, it says, okay, I know this is completed. So you can actually do queries of the database to figure out what's your current progress, for example, in computing. So this is the type of thing that MongoDB can do for you. And the other great thing is that essentially in one database you have your input data for the queue, you have the mediation of what's being processed right now, and you also have the results for your queue. So it's a really integrated system that's very simple. All right.
So did you have to deal with various kinds of exceptions? Like suppose extractor goes off and just doesn't return or has an error?
Yeah, so essentially then you have it so it doesn't actually put a result into MongoDB. And so then you can query for that and say, oh, I know that this image doesn't actually have this field. And so then for the next step, you'd actually want to do an exists to make sure that the source extractor step actually puts something in the database. And so you can put in an exists operator essentially saying, I only want to work on stuff that I actually have data for. And then for the ones that were exceptions, you can have query for the ones that didn't work, and then you can figure out why that didn't work, right, in addition to the normal logging process.
So you do something when something fails. You put them in a failed stash or something.
Yeah, exactly. It would be, what you would do is you would query for, so in this case, you would actually build a query for exists and then 0 for false for this scamp.sourceExtractor path field. And that would tell you the ones that didn't work. And then you can process them separately.
But was then though? I mean, you had a job, right? And
yeah.
What happened to the job when it failed? Did it just evaporate? The only trace of its
existence. Oh, sorry. In terms of the queue here.
That's right.
Yeah. So what you would actually want to do, if this was like full, industrial strength code, is you'd actually be wrapping this in a try except, and then catching that exception, and then you would have. And then instead of having this general update of task.complete is true, for an industrial, robust code, you would have what exception was thrown, for example, as a field in your database. And so then you can query for those. Yeah.
What about the more insidious problem if it finishes, it just gave the wrong answers?
In terms of like scientifically?
Photometry. Like you run this code, or the astrometry, you run the code and it should be at 0 hours and plus 40 degrees, and it ends up being at 12 hours and minus 26 degrees, but it finished somehow.
Mm-hmm.
How do you deal with those?
So I don't have a system for that. Essentially, the next step will fail, and so this is sort of the problem.
The mosaic was like
so this is this is the thing is that is even though I'm building a pipeline, the pipeline is so that I can go back, change, build better code that fixes all these problems, and then rerun things. So rather than having something that can stream through all the data that's coming through the telescope, why I'm building a pipeline is actually so that I can reprocess things when I know what to do, when I know that I have to take care of some problem. So essentially I would know the next step would give me some weird result, and so I know that I'd have to actually go back and reprocess things. And so that type of science validation comes down to sort of the wetware of the grad student, I guess, just knowing this isn't working. Yeah. So again, this is the sort of thing of it's a slightly different world of just having a single grad student compared to an observatory, but it's sort of moving that single grad student into this world of slightly more robust code and systems. If that makes any sense. Okay. Okay, so now I'm going to get into more of the actual reduction algorithms for this project. So one of the key questions is how can you actually do sky subtraction over such a large area of the sky if you can't actually measure the sky in situ on the disk, of course, because your entire image field is covered with M31. So with MegaCam, MegaCam has pretty pristine reduction codes. But if you get a flat-fielded MegaCam image and you want to do surface brightness photometry across it, what you'll realize is there's actually a massive center to edge background variation within it. And this is all due to scattered light, which is variable depending on telescope orientation, where the moon is and where sources are and so forth. So this background actually changes, and so you need some way to subtract this. So what we did was we actually took near-infrared observing techniques where you can't, of course, measure the actual background in situ within a field because you have you actually have signal within that field. So you need to actually do sky target nodding. So with MegaCam, our approach was to have 14 MegaCam fields covering the entire disk footprint of M31, and then surrounding that were 8 sky fields. We would do sky target, essentially sky target, and then another target, and then going back to sky. And then we would do this cycle such that we could queue in a continuous sky target nodding cycle through the entire footprint of M31 in about an hour. And so this let us actually queue this with CFHT's queued observing mode such that they could guarantee that they'll complete this entire observing sequence without interruption. And then to build a deep mosaic, then we just repeat this sky target nodding cycle but with dithers so that we can build up a deeper mosaic on individual fields. And so doing this, you can go from MegaCam frames that have lots of scattered light, build real-time backgrounds over this 1 hour window, and then background subtract and get pristine images. And so that's what actually lets us, for example, with MegaCam, see things like the northern spur, which is a really low surface brightness feature, tidal feature in the M31 disk, now in integrated light, beyond just the resolved stars that other surveys have seen.
So what's changing in an hour that you go back to the sky so frequently?
Sorry?
Why do you have to cycle back through the sky several times?
So potentially the sky itself is changing.
So atmospheric.
So you have like the atmosphere, and then you also have potentially the detector itself. Something within the telescope is changing. And so it's not as bad as in the near infrared where you want to have like a truly real time, like within 5 or 10 minutes sky background update. But what this lets us do is, as we're observing the disk of M31, like over that hour, we can build up some model of the sky or of the instrument background, and then subtract that. Yeah.
But your sky fields,
they're fairly close. Is that what you're asking?
Well, no, I was actually thinking the opposite. That on the northern side, you're starting to run into the Milky Way, and on the southern side, you're running into the halo, and so your bottom right field and your upper left sky field are going to be very different. So how do you deal with that?
Well, we use the sky level determined just by this. So in terms of the sky being variable over, the physical altitude azimuth sky. So I use this sky, like the scalar sky level associated with the closest sky observation. But then as far as the Milky Way, that essentially that goes into resolved stars that we can mask as we're building the background model. And so that's something that effectively marginalizes out. So that hasn't been a problem. That answers your question. Now in the near-infrared, the situation is a lot more dire because, first of all, the near-infrared sky is bright. So at the edge of the disk of M31, the sky is 1,000 times brighter than the M31 disk. And beyond that, it's also extremely variable. So I'm not sure if you guys have seen this picture, but what they've done here is they've actually used a 2-mass camera and then just attached it to an off-the-shelf camera lens. And we're looking at the 9x9 near-infrared sky, so the H-band sky. And so this is elapsing over about 2 hours, so it's 500 times speed up. And so the immediate thing that you learn from this is that the sky that you observe in the sky field here has almost nothing to do, to some extent, with the skies you're seeing on the disk. And so observationally, I tried lots of different methods for dealing with this type of disconnect. The obvious thing is to speed up your cadence. So we went sky target, sky nodding, every 2.5 minutes, for example. And since there's obvious spatial variations in the sky, I even tried pseudo-randomly selecting from different sky fields around M31. So that's what this ring of sky fields is here. So I'd go to a sky field here, go to the disk, and then go to some other pseudo-randomly selected sky field. And the hope was that I could marginalize over different shapes of the sky background as I was building a real-time, median background model. But ultimately, no matter what you do, I found that you couldn't actually know the sky to better than about 2%. of the sky level. Now, given that the sky is 1,000 times brighter than the disk, this is an obvious flaw. So just doing sky target nodding, building real-time sky backgrounds, this is the type of picture you get. So you can see the bulge of M31 that comes through. So that's what 2MASS saw. This is essentially 2MASS quality. But then you quickly lose the disk in sky subtraction residuals. So to move forward, well, you can sort of make, you can realize that the flaw with this image that comes to mind immediately is there's discontinuities in the surface brightness across from field to field. So let's just write an optimization such that we solve for offsets of flux for each frame in our mosaic, such that we move one up in surface brightness a little bit and one down in surface brightness. And then for all the overlapping pairs of images, there's optimally 0 surface brightness difference. And so this is the type of optimization that we've done. And if you use Montage, they use a similar process. For them, they've used an iterative approach where for each field, for each pair of fields, they solve for sky offsets and then iterate that iteratively for every pair, and they keep doing this over and over until they converge. The approach that I've used is to use just a downhill simplex code, but then with lots of precautions for getting a globally optimal fit. So reinflating the simplex when I've found a solution, letting it converge again, and then also starting from different points in parameter space. But the main challenge with this type of optimization, even with Montage, is there's just so many parameters to the optimization. So we have several thousand individual frames that each one we have to solve for a sky offset for. So the solution to that is you can identify a natural hierarchy in this problem. So we have 39 fields across M31 with WeirCam. Each field, WeirCam is a square 2x2 detector array. So within one detector, it's looking at the same part of the disk of M31. So you can just, with a linear equation, solve for the sky offset that brings all these frames to the same level. And then now you have a 4x4 or 2x2 set of these frames, and then now you can do this optimization to bring those to the same level. And then from here you have 39 of these blocks, which now at worst becomes a 39 parameter optimization to get a continuous surface brightness mosaic. And so what that does is it gets you to images that look like these, that are a lot more continuous, but there are still flaws that I'll get to in a moment. One of those flaws is that these sky offsets are about 2% of the sky level. So we're moving the surface brightness of this mosaic up and down, and there's still the question of what's the absolute normalization of the surface brightness. So that is about like a 2% divided by the square root of the number of field type uncertainty. And so that's enough that you can actually massively over-subtract or under-subtract the sky of the disk at the edge. The other flaw is that there's actually an instrumental background within WeirCam that no one knew about before that varies from frame to frame, and you can't build a model of that. And so that's part of the reason why we have these discontinuities that remain at the 0.1% of the sky level or less.
What was this? Was this a readout, or where did this come from?
So you can actually build sort of if you build sky flat type frames over time, you see these sort of blobs across the detector that move over time. So it could be a thermal background. It could be.
You should have come to the other telescope. Carry on.
It's true. It's true. So WeirCam, So what do we do? So we still have this mosaic. We can't get science out of it. So how bad is it? Well, you can take a surface brightness cut, so just a wedge along the major axis of the disk. So here we have U, G, R, I, J, K. And you can see the K band is dying very quickly past 10 kiloparsecs, and this is no good. Even the I band for MegaCam, just from the sky offset optimization we have to do there too, it can be over-subtracted, at about 20 or 25 kiloparsecs. So you can't do SED analysis if your data is doing this, essentially. So what do we do? Well, we realized that the goal for having images is to be able to do spectral energy distribution modeling. So we're Bayesians, and so you can write down some sort of likelihood function to model your SED. So here's a Gaussian likelihood function. We have the observed, SED in each pass, or flux in each passband compared to some model from a cellular pop code. And then wouldn't it be nice if you could actually have a term in this likelihood function for a background that you want to model? But now for a single pixel, this is entirely ill-constrained. because you can't model a background and the stellar population. It's totally degenerate solution space. So we can step back again and say, well, what are we trying to do? So with these types of likelihood functions, you can draw probabilistic graphical diagrams. And all this is doing is it's just showing how information flows within your hierarchical problem. So we have the observed SED, and essentially this observed SED is dictated by SED uncertainties, and then also so uncertainties, but also it's driven by the actual astrophysics of the stellar population we're observing, and then the parameters of that stellar population. So we have a single pixel, and we can model that flux. What if we have lots of pixels? And let's say that all of those pixels have independent star formation histories because they're covering a wide area of the disk. So each pixel is independent. So in the shorthand of these PGM diagrams, you can just draw a box around it saying that we have lots of these pixels, but they're all independent. And now let's say that we're covering a large swath of the image. They have different stellar populations in each pixel, but overall, all those pixels are affected by approximately the same background subtraction error. So we can have another level in this model where we have a global background in each passband that affects all the pixels. So now we have essentially a hierarchical problem with two levels of a local stellar population modeling problem and then also a global background subtraction problem. And so that's exactly what we've done, build this hierarchical model. Now to estimate the parameters, so stellar population parameters and background parameters in this model, we're using Markov chain Monte Carlo, which is essentially a technique for estimating parameters in a model by stepping through parameter space, and then where you step, like the amount of time you spend in different parts of parameter space as you step through it, reflects the underlying likelihood functions. So the problem with this type of model is it's a huge parameter space. You might have 10 parameters defining a stellar population for a pixel, and then you have, say, 100 pixels. It quickly becomes a very large parameter space to be stepping through. So you run into the cursive dimensionality type problem. So one way to navigate through this is to build a Gibbs sampler. And what the Gibbs sampler does is it lets you step through parameter space one piece at a time. So in the base level of this Gibbs sampler, what we do is step through the parameter space for each pixel. And remember that all these pixels are independent, so you can actually, for those 100 pixels, you can fire up 100 cores and then step through them in parallel. So this becomes a scalable problem. And so we essentially step through the parameter space for each pixel to get a new estimate of what the stellar population of that pixel is. And then the next step is we aggregate all those results, and then we ask what's the residual between the observed SEDs, so the observed flux in each passband, and the model we get from that point in parameter space. And then let's assume that that residual is only due to background subtraction errors. So for each pixel, we get some estimate of our background subtraction error. And then we can draw some Gaussian distribution that reflects the variations in the different residuals. And then we can use that Gaussian distribution to then sample from to estimate a background correction. And then so we get a background correction here for each passband. And then with the Gibbs sampler, you then feed that back up again to your lower level. So for the pixel level, you then step in stellar population parameter space, and then again you go back into the background level of your hierarchical model. And so you repeat this thousands of times, stepping through the stellar pop and the background parameter space. And then you get chains of estimates from all of these. And so the chains look something like this, where essentially you're moving within some distribution function for all the backgrounds. And then you can estimate the median and the uncertainties of that background. And then you can then apply that correction to your pixels. So here is our original SED. So we're looking at the SEDs of individual pixels along this major axis cut, and then we're running our hierarchical model across all of the pixels along this radial wedge. So this is radius through the galaxy from 0 to 30 kiloparsecs, and then surface brightness. And then with our correction, then we get something like this, where the K-band, it was over-subtracted here, it gets boosted up because this is the background we identified, and now it has approximately 0 color with respect to the J-band. And this is actually what the stellar population tells us, is that J minus K and AB mag should be about 0. So we succeeded there. And then you also see that the I-band, we also estimated that we were over-subtracting. And so the I-band gets boosted up, so it's again slightly brighter than the R-band, which is again consistent with a truly physical SED model. So essentially what we're doing is we're correcting the background in such a way that we get a sensible physical stellar population model. And this is essentially what we have to do to actually move forward with this technique here. All right, so with these corrections, sorry, I'm running a little over time. You can then actually analyze M31 and look at stellar populations. So I'll just give you some sneak peeks of what we're doing. In every radial wedge bin across M31 here, we're estimating the mass-weighted age of the stellar population. And what you find is this beautiful gradient of age across the disk of M31. So again, this is radius versus the mass-weighted age in gigayears. And you find that the bulge of M31 is old, as you'd expect. So here it's we estimate about 10 gigayear stellar population, and this nice gradient in age inside out. So the outside of the disk is younger. And then what's really cool is at 10 kiloparsecs, if you've looked at M31 a lot, you'll remember that there's this ring of star formation going on at 10 kiloparsecs. And the Hubble Andromeda Treasury Survey has found this is actually a fairly stable structure with stars that are within that ring that are 500 or gigayear old. So this is a stable structure. And what we're actually finding is there's a break in the age gradient at that 10 kiloparsec ring, which is really cool because it could mean that there's some secular evolution process where within this ring we're bringing material into the bulge, and then there's some shallower stellar population gradient outside the ring. So this is a really cool result. And then the two lines here just showing what happens if you have different content in your model. So the orange is only if you have optical passbands, and the green is if you have optical through near-infrared passband information.
Is there any physical explanation as to why that would happen?
Yes, so you could have essentially. So essentially, the idea is in secular evolution, you can have like a resonant, like an outer Lindblad resonance, that type of thing, where stuff moves out or in from that resonance, and so that would be the idea. Yeah. And then there's some indication that M31 should have secular evolution because it has somewhat of a bar structure that you can see in the near infrared as well. So we're sort of painting this picture of a galaxy that forms inside out, but there's also on top of that internal processes we call secular evolution that are moving material across the disk inside and out. In terms of metallicity, we also get this really interesting result of having. So this is metallicity with respect to the sun. So this is solar metallicity at this level right here as a function of radius. And the bulge, as you expect, is really metal rich, so it has lots of epochs of star formation that have gone into the bulge. And there's a gradient towards more metal poor stellar populations going out. And we can see here that actually fitting stellar metallicity through SEDs is extremely difficult, just because it's so sensitive to the color of the stellar of the SEDs. So the optical and the near-infrared fits disagree quite substantially. But again, the really neat thing is we can also compare these fits with resolved stellar populations with spectra, and then we can analyze exactly what are the degeneracies and biases of SED fitting compared to other methods. Because essentially this is what you can do with all the galaxies in the LSST sample, for example. So what are the biases when we actually look at all these unresolved galaxies with LSST? And then mass-light profiles as well. Lots of people assume there's a constant mass-light ratio for M31, but there is a gradient to the stellar population, so there's a gradient in the mass-light ratio across the disk. Now, one thing for the M31 aficionados, you may wonder, how does this correspond to resolved stellar populations precisely? And so, for example, Brown et al. Used the ACS camera on the Hubble Space Telescope to look, at the resolved stellar population going below the main sequence turnoff to get really accurate ages and metallicities. And so they find a mostly 6 gigayear stellar population, which is a lot older than the approximately 4 gigayear stellar population we see at that radius. So what, is it that SEDs are wrong, or one possibility is that actually resolved stellar populations are also wrong to some extent. And so this was a project that we've been involved in, Stefan and some collaborators, is actually looking at are we estimating resolved star populations wrong as well? So to give you an example of this, here we have really clean photometry for an open cluster, NGC 188. And what they're showing is that if you fit, traditionally only 2 colors in this CMD, so normally when you're fitting resolved star populations, you're looking at the color magnitude diagram space and you're fitting in that CMD plane, so you only have 2 colors. What they're finding is that if you only fit in the CMD plane, you actually get substantially different results than if you do a Bayesian model where you're actually looking at the SEDs of individual stars and then trying to model those individual SEDs compared to only fitting 2 passbands. So perhaps it could be that our methods for interpreting resolved star populations are also wrong. So there's some interesting comparison here. And then different isochrones also give completely different results. You get completely different results in metallicity space as well. So this is the type of work that we can do with M31 because we now have data sets for SEDs, for resolved stars, for spectra as well with IFUs coming online, where we can actually figure out what are the biases for all these techniques. All right, and then I'll just point out that we're doing resolved star populations as well, a little over time, but this is what our J-K color magnitude diagrams look like. And then if you're wondering what the Milky Way looks like compared to M31, well, the Milky Way is all this stuff at the bluer part of our color magnitude diagram. So you can actually, in the near-infrared, cleanly separate those. All right, so in summary, what we've done here is we've mapped the entire disk of M31 in the U through K bands. So we've covered 14 square degrees of the sky. So we now have essentially this homogeneous data set. We now have a picture of M31 we can analyze like any other galaxy in the sky. And so we're already seeing these really dramatic stellar population gradients, which is really interesting scientifically. And then we can also, the next step is to actually compare what we see in SEDs and resolved stars, so color magnitude diagrams, to identify what's the bias of each type of analysis. Now, technically, the key challenge has always been background subtraction. And so again, the solution to that was to have this threefold pipeline, or this threefold calibration method of first go to the telescope and then do really rapid sky target nodding, which gets you to about 2% of the sky accuracy. Then you do mosaic optimization, which gets you down to about 0.1% of the sky. And then from there, the only recourse is to this hierarchical SED modeling to actually get truly well-calibrated SEDs that are consistent with having an astrophysical stellar population. But the thing that I also want to highlight is that to actually do this data set, to have one grad student essentially get all this data and process it, I've had to use tools from industry. So MongoDB, the star catalog is also based on SQL using PostGIS to do spatial merging as well. You can ask me about that later. So we've actually used this type of technology to help with the processing. And everything is within a Python pipeline, so again, everything is within an integrated environment. Everything is reproducible, redoable. There are no steps that are done by hand. So that's really the key for this type of work. And then, in particular, MongoDB is actually really useful for the single or small teams of astronomers because it's an agile database. It lets you do essentially anything quite quickly. Yeah. So I just want to do one brief thing to ask, what can we actually, how can LSST help this type of astronomy? And this is the thing that I'm really excited about with LSST, that you're building this stack that now anyone can build off of. So essentially, LSST is becoming the framework that was missing for the medium data pipelines of astronomy. And of course, LSST represents this industrial scale of astronomy. And to date, everyone's been working, in these fields with your goats, in small teams working on really agile projects, just going from one project to another. And this will never change. We'll always have professors and their grad students working on projects. But the key is that we can't keep doing this. We need to go into this industrial era. So I just want to point out, what are the things that LSST can do to help, this scale of astronomy, which will never go away. So the first key is we need trustworthy data. We need, as observatories, we need to give trustworthy data to the scientists. And you guys here, I know that you're doing this already, but a lot of observatories aren't. So we shouldn't be instrument scientists if we're astronomers. We should be able to trust our data and actually know what the systematics are and have everything fully documented. since the observatories have, the data, have the compute power, they should be able to actually reduce data better than most grad students. So things like star catalogs, galaxy catalogs, observatories should be able to do. But the challenge for this is actually making sure that you're giving the astronomers the right types of data. So, for example, observatories can produce star catalogs, but if you want to fit color magnitude diagrams, what you really need is, in addition to a star catalog, you need to know what stars aren't in the star catalog. So you need results to artificial star tests. And these things are hugely computationally intensive, so it's a big challenge to do that as a grad student with your university or department compute cluster. The observatories can do this, and so the challenge is actually knowing exactly what astronomers are doing and what they need to provide them with that. But I think, with L3, I think you guys are really doing the right thing, and so I want to be part of helping make sure that happens. The other thing is that, the big observatories need to speak the astronomer's language, which, I'll just be bold and say Python. For the life of LSST, observational astronomy will be done in Python. 2.0. And so, what that means is that, and the reason that's true is because Python is an environment where you can do everything within it. You can do your numerics, and then you can build your web app to show your catalog. So you can do everything within Python. You can integrate to other tools, so it's a flexible language, and that's why it's used for observational astronomy. But what that means is that every product that LSST provides, it needs to have some sort of Python module that you then import to do your work. So essentially, people shouldn't have to write their own wrappers for a web API. LSST needs to provide that Python wrapper. So essentially, everything needs to be importable from someone's IPython notebook. If there's a database, you need to do it the Pythonic way of actually providing an SQL type package so that people actually can query from it from within Python as well. You shouldn't have to go to a web form, type in your SQL query, get a table, import that into your IPython notebook. You should just be able to have in your IPython notebook the query statements, get the data, and then just work within the notebook. And you need to be Pythonic. So it means, the Python community is a really picky community, and we know what good code looks like, and we have these standards. So it's really important to actually follow within that sort of community and those sort of Pythonic standards. So things like how docstrings look, how things are named, how things are, having these magic functions. So proper wrappers, proper IPython notebook magic functions. You can have, units in the values that something prints out when you have it in IPython. Those are things that Python programmers expect, and they need to be provided. Python programmers also expect things to be easily installed, and so I know that's going to be an interesting challenge. So things need to be easy to install, and so things should be pip installed. And so what that might mean is that if we can't do that right away, it means that some functionality could exist outside the LSST stack. If you need to interact with the database, if you're just the average astronomer, you want to get some LSST data and you don't want to install the entire stack, maybe some of this interface should actually be an AstroPy, which everyone has. So we need to think about actually integrating within this whole SciPy, AstroPy community, and not just being an island within the LSST stack. And then the other thing is computing infrastructure. And so it's been awesome talking to you guys, because I know that you're all on the same page here. Is that grad students, we start stuff on our desktop, but then we quickly run into the problem of, oh no, we need cluster compute. But the problem with this is now you have two completely different environments. You've got the files on your file system on your own computer. You can buy lots of hard drives. But then now all of a sudden you have to go to a cluster, and that's an entirely different environment. Your files aren't there yet. And so actually going between your desktop and then going to the cluster and then getting those results back, it's a massive friction point. And people shouldn't have to think about that. It should be that you just write your code and it works on your desktop, it works in the cluster without you having to really think about that. So that's the ultimate goal of the future, I think, that we can work towards. So essentially, everything should be cloud-oriented is the idea. And then we also need some way to actually host these data sets. So if I could create an Android star catalog, where do I host it such that you can query it? So we have astronomers needing to produce web services. And how do we exactly provide that? So we need to have some sort of like an Amazon Redshift for astronomers, but actually make it so that the average astronomer can host their database on that. So I know that, I think this is in the culture of LSST to do, and this is sort of where I see astronomy needing to go. And so I think it can be fantastic to help make that happen. So thank you for listening, and I welcome any questions.
Fantastic, thank you. Excellent. So folks, hang on, I'm going to give anybody remote a first go at this. Does anybody who's dialed in would like to ask a question? Unmute yourself and go for it, and we'll let you go first.
Nice to meet you.
Anybody from the outer cloud sphere? No, going once, going twice.
I have questions.
Okay.
Yeah. All right.
All right,
So
Josh.
this is probably a very naive science question, but in the modeling estimate of what the background should look like based on stellar populations, how does that deal with objects in the background, like for example, faint galaxies and stuff like that? I mean, that's got to be some sort of source of contamination. So do you see structure that comes out from that, or?
So far the pixels that I'm working with are large enough that essentially marginalized out by the more dominant M31 light. So if you have a background galaxy popping up through the disk, right now my pixels are still large enough that those essentially get medianed out. A real challenge though is all those Milky Way stars, which if you look at the colorimetric diagrams, they are like a massive source of light in the outer disk. And so for those, to first order, I've masked them out using just color cuts from the 2-mask catalog, so I can build, masks for all those types of stars. And then for the scattered light in the megacan halo, then I do masking by hand. But something more sophisticated may have to happen to that type of contamination. Absolutely.
The PSF is probably different or something for the stellar objects, right?
Yeah, so what I was talking about was that, okay, it's not going to come up. As if I can find a megacan image here. So the megacan has all these, extended PSF halos and faint surface brightness. And so the key is that right now there's actually no optical model for these. People have tried to do ray tracing through the megacam optics, but there's actually no reproducible model for these, for all these scattered light surfaces that show up in the images. And so that right now this is all masked by hand. And so the trick though is you can have extended halos that actually are really insidious that you don't see, but they're still affecting the background, the level that you're actually trying to work with astrophysically. So that's still a challenge. Yeah.
So the other question I have was about provenance. So say I'm going from a complete assembled mosaic. Can I construct a query that will go back through Mongo and give me the complete provenance of all of the steps that happened to assemble that mosaic?
Right. So the provenance right now is basically, it's naive because it's just one grad student doing this. So I'll always qualify my
How would you have done it given infinite resources?
Given infinite resources.
There's 50 people.
Okay, because essentially right now, I know the provenance because I can make sure that everything is run cleanly through the pipeline, so I know consistently. But what you could do with MongoDB is I have really simple fields right now, but you could of course augment these fields with embedded documents for every piece of data that goes into here. So you could have an embedded document that says, here's the git commit of my stack, here's the time it was processed, here's where it was processed. In addition to the actual data itself. So you can essentially have metadata within the metadata. And then the cool thing about MongoDB is there's a thing called a SON manipulator, a serial object. I forget what the N stands for. But what that does is that you can have these structures within MongoDB, and then when you query for a field and you actually get the field out of PyMongo, like the Python MongoDB wrapper, it'll give you an object. And so that object can then have all your provenance information within it. So you could have the value, but in addition to that, you could have attributes, for example, with all this metadata inside it. So you could have a really nice solution that way. And I've also thought about for storing data, like everything's on the file system right now, one thing I could do is also have a structure that tells me where it is on some other server, so I know where I can download it from, for example. So right now, you could sort of think of all this metadata as being sort of naked, but you could actually have structures around all this metadata quite easily. Yeah. So that's how I would do it if I redid the system. Yeah.
Can I just, well, we could just wrap up and take some lunch for the local people. So, remote people one more time. Okay, well, thank you very much. Thanks for calling in, people. And I will send around the offline viewing link to the MDBell later. Thank you very much, Jonathan.
Great, thanks.
Okay, bye.